Now we've talked about the currents generated in a loop of wire as the magnetic flux changes within that loop of wire. But in reality, what if we don't have just a loop of wire? What if it's a solid object or a conductor? Well, what will happen then is motional EMFs, again changing the magnetic flux through some area, can create current loops in conductors. Now, of course, in a loop of wire, that's just current in that loop of wire. But in a solid conductor, what happens inside the conductor is current will flow. Remember, current is free to move in a conductor. It usually randomly moves about. So if you have a big block of iron, for instance, or a big block of copper, then electrons just move in random directions very rapidly, these conduction electrons. If you place it in a changing magnetic field, what can happen is those random motions of electrons become sort of a current, a flow, almost like a flow of water, if you will, in a river or an ocean, a current in an ocean. The electrons will actually move in very specific directions, creating usually loops of current. These currents are called eddy currents. Now again, these are not currents like water, although you can have eddies, of course, in water. These are loops of current, of electricity, inside solid conductors. Now, where does that energy come from? In both cases, for instance, right? When I change the magnetic flux, for motional EMF, when I move that bar side to side in the previous example, current flows. But to generate current, you need to do work on electrons, right? You're pushing the electrons through the wire. Where does that energy come from? How can you push electrons through a wire? Well, it comes from the source of the motion itself. So physically, if it were me pushing and pulling on that bar, then the energy generated by those currents come from me. In other words, that bar actually has some resistance, even if it were frictionless. There's resistance to me pushing and pulling that bar because I generate power. So a simple example. This is a very simple electric generator. It's attached to 4 little light bulbs. Now, when these light bulbs are secure, as they are here, apologize if I goof this up, I don't want to break anything, I can spin the generator and you see the light bulbs light up. This requires work on my part. This is hard to turn. You can see that if I just give it a little push, it quickly dies. But if I unscrew these light bulbs, so they're no longer part of the circuit, so now this isn't a complete circuit anymore, this becomes super easy to move. Wow. I can just give it a little push, and it goes around multiple times. Because I'm not doing any more work on this system. I'm not pushing the electrons through this circuit anymore. Therefore, it becomes much easier to move. Almost, I mean, the only thing that's slowing me down is friction. If I plug in half of the light bulbs, it's easier to move than when I have all 4 in, but it's more difficult than when I have nothing in. If I put all 4 light bulbs back in, it requires quite a bit of energy on my part to generate this. So I do the work. Literally, by spinning, you can't see it inside here, there's a rotating magnet, rotating coil of wire in a magnetic field generating this motional EMF. That motional EMF, that work comes from me. There's a wonderful video online, I'll try to link to it in the discussion, of an Olympic bicyclist. So a gentleman with just enormous legs, right, who's a professional high-speed bicyclist, actually powering a toaster. So rather than me just spinning this around and having the lights go on, he actually pedaled to produce 700 or so watts of power, which is what a toaster oven does. And the question was, could an Olympic bicyclist, using his very powerful legs, power a toaster to make a simple piece of toast? And the answer is yes, but just barely. So it requires a great deal of energy to do these things. So for motional EMFs, rather than having a physical generator like this, we either have a gasoline engine, like for the generators you can buy in case of emergencies. that's powered by gas leads an engine that creates motion. That motion generates electricity. Or steam generators for old trains or nuclear coal power plants usually power steam generators. Those turbines spin, generate power. Wind turbines obviously spin. That rotation generates electricity, motional EMF. Water wheels, on water turbines for hydroelectric power. So motion can be changed, kinetic energy can be changed into electrical energy. Again, energy cannot be created nor destroyed. It has to go somewhere. Now, to show you again what I mean by eddy currents, your book uses the example of a pendulum that moves in and out of a magnetic field. And as it moves into and out of the magnetic field, eddy currents are produced, which reduce the oscillation. It's kind of like friction. Again, it takes energy to make those currents. The only place that that pendulum can get the energy to create those currents is through the kinetic energy of oscillation. So the kinetic energy of oscillation is reduced, the pendulum slows down. I just want to work out a more simple example of what an eddy current is. So in this example, I have a magnetic field going into the board once again. And instead of a loop of wire, imagine this is a solid copper cutting board. A little handle cut out here on this end to help with that illusion. So just think of a cutting board that you have at home, but make it out of a conductor. Make it solid iron or solid copper or solid aluminum. Now the magnetic field in this example ends at the dotted line. So there's a magnetic field in this area of space, and here's the border, and on the right of this dotted line, there is no magnetic field. So as this cutting board gets pulled to the right, the magnetic flux through the cutting board diminishes, right? There's no magnetic field over here, and as I pull it to the right, the area of the cutting board, area A here shown in the orange hash marks, area A gets smaller with time as this moves to the right, which means that the magnetic flux is changing. Because the magnetic flux is changing in this conductor, an EMF is generated. That EMF generates a current that opposes the change in magnetic flux. So in this case, again, a clockwise, like with the loop of wire we did in the last example video, a clockwise current forms inside this cutting board. But this cutting board is not a wire. Current doesn't just flow along the edges. The current actually swirls around inside the conductor itself as I'm pulling this out. The faster I pull it out, the bigger the current that I get and the more resistance I would feel. So moving this cutting board, just if it were just empty space, if I pulled that cutting board out, there'd be almost no resistance, right? Just moving a cutting board in space doesn't do anything. But if this were, again, a conducting solid copper cutting board, and I pulled it out of an intense magnetic field, it would be difficult to pull it out or push it in to the magnetic field. So we have these example of these eddy currents. Now, your book uses, again, the pendulum. There are practical applications to using these eddy currents, analytical balances, very precise balances that have the scales that rock back and forth. You want to minimize the friction in those scales, right, to get an accurate balance. But at the same time, if you minimize the friction, then the scales will just oscillate forever, back and forth, back and forth, back and forth. You don't want that to happen, so by placing an induced EMF in a copper plate, those oscillations can be dampened through these eddy currents, which can then, so you can put current through the circuit, stop the scales, let the current go, let the scales balance, and they might tip one way or the other, but it reduces the oscillation. You can do magnetic braking in elevators and things like that, but it requires motional EMF. So the object has to be moving. So a stationary elevator cannot be, the brakes can't be applied in this case. But if you have a fast-moving object and you want to slow it down, then these eddy currents and magnetic dampening is a way of doing that through the induction of currents in a conductor.